This is a chi-square goodness of fit problem because we want to see if the observed frequencies match what the city engineer believes they will be. Our variable is the direction that cars are going to go if they're on Front Street approaching Elm Street. Are they going to go straight? They're going to take a right turn or a left turn. So we have three categories, categorical variables, three categories. Our null hypothesis is going to be that the observed distribution matches the distribution predicted by the city traffic engineer. Our alternate hypothesis is going to be that the observed frequencies do not match the frequencies that would be predicted by the city traffic engineer. So we had our total. First we need to know the total number of observations, and that's 200. If you add 112 plus 48 plus 40, that's going to give us 200. So our total is 200. We have our observed frequencies. We observed 112 going straight, 48 turning right, and 40 turning left. What we would predict if we had 200 cars and half of those 200 cars went straight, that's what the city traffic engineer believes. So that would be 100. So we would predict that 100 went straight. And of the 100 that are left, half of those went right. So that's 50. This is what the traffic engineer thinks. And we're going to have 50 of those 200 going left. Because right here we say the city traffic engineer believes that half of the vehicles will continue straight, and of the remaining half, equal will turn right and left. So that's how we get our predicted frequency. Now, we need to calculate the chi-square value. That's our test statistic. And chi-square is equal to the observed count minus the expected count squared divided by the expected count. And we're going to calculate that for each of our categories, straight, right turn, and left turn. So for straight, we had 100, and I'm sorry, we had 112, my bad. This is what we observed. We expected 100. And so we've got 112 minus 100 squared over 100. For the right turn, we've got 48 minus 50 squared over 50. And for the left turn, we've got 40 minus 50 squared over 50. If we do that calculation, it comes out to 3.520 if I round to 3 decimal places. Now for this problem, the null is going to be rejected if chi-square is greater than some critical value. And so we need to look at our table. If we draw the picture, the chi-square distribution looks something like this. And our critical value is going to be right here. If this area, our critical value is going to be the chi-square value that would give us an area of 0.1 because that's the significance level that we're using. And so we're going to go to our chi-square critical value table. And if I look at the area, this is what the table looks like. You can find them online. You probably should have one. So if I'm looking at the tail probability of 0.1, and my degrees of freedom are 2, because, sorry about that, degrees of freedom are 2 because I have 3 categories. The degrees of freedom for chi-square goodness of fit is number of categories minus 1. And so with 2 degrees of freedom, and 1% or 0.1 significance level, 10%, the critical value is 4.61. So if my chi-square is greater than 4.61, then I'm going to reject H naught, the null hypothesis. And remember, our null hypothesis was that the distribution that we found matches what was expected by the traffic engineer. Our chi-square value of 3.520 is not greater than 4.61. In other words, ours is somewhere like right here. So that's in the fail to reject region. I'm going to reject if my chi-square value is in the shaded region. I'm going to fail to reject if it's in the open region. So we're going to fail to reject. We have no evidence that the city traffic engineer is not correct in his belief that half the vehicles will continue straight, a quarter turn right, and a quarter turn left.